we got stuck at some point in the contest. That's reasonable because just more medium problems, so that you can just have to work it. You should work it a bit more for each one of them. I saw some of you had some trouble with the one that I thought was rather simple, which was bars. And I can see three expressions are the same, so I'm going to be very short review of how you can go with the bars. So that's something I showed about. So that's last time I was here. Usually it depends how much I talk about this, and it depends on how much you know about this. You just, if I go too slow, just say, I know everything, and I can move fast. But just let's spend like a few minutes on that, and then we can review the problems from yesterday and any problems we want from other days. Also, today's contest is going to be sort of different because I'm going to put a lot more problems, maybe more than usual. The idea is for you to have fun. That's my goal today. There's going to be problems for everyone, for every day, backtracking, strings, geometry, whatever you like. It's going to be there. So you can just have a bit of fun. Don't like a problem, don't even read it stuff anymore. I hope you do some of them. I like these problems today. I think they are many, but they touch a lot of subjects. Something that I haven't talked about today. So you should try to solve them, and if you can discuss with me, or like a mail or something. Or you can just keep them in your head and try to solve them at some point in your life. That will maybe point towards something about studying or something about the question. Okay? So I hope you are not waiting for very long. Because I can contest either to the one like to final or finals or something like that. It's not really a bad contest anyway. So as I said, you should have fun. That's why you're here. Have fun. It will be nice to so on to the problem. I say some of you had trouble, and I thought it was a sort of easy problem if you know how to implement things right. It was the one which was called equivalence. So it was basically they give you two expressions, say A plus B minus 2, and A 2A plus 2B. I have to say they are equal. Okay, so in this case they are obviously equal. But maybe you can have multiplication stuff. B plus B here, 3 minus 2, and then plus that 0 minus A. Things can get sort of. I didn't have one of mine, right? So things can get a bit complicated, and in order to see if these two are identical or not, you have to be able to understand some expressions. So I will try to show you a way you can parse these expressions. And that means follow the structure they have, because our structure is expressions. They follow rules, and if you can follow them, then you can evaluate these expressions, and then you will be able to code whatever you want. Maybe you want to check if the expression is syntactically correct, or maybe you want to evaluate it with some values or variables or whatever. Okay? In this case, we want to check they are equal, then let me see how we can do that check. But before we have to understand how to deal with stuff like this, which you should think of it as coming in a string. I don't know what's going to come, so maybe I just use get all the input in my string and then see what I can do with it. So in this project in particular, there could be white space in between, so that's something we're going to deal with. There was also the fact that uppercase and lowercase letters were similar. So one way to do this is try to sanitize your input before you're starting to work with it. Okay? So let's say you have this and this. To read it, they came in different lines, so you can use maybe C get line. Here you get the buffer. Here you get the size. So let's say I use as a buffer chart. I think they were sort of short. Let's say 500 characters. That would be a really long mathematical expression to evaluate by hand, but for a computer that's fast. So you would use to read each of them like this. So let's deal with one, and then we'll see dealing with the second one. Okay. So we actually write a general parser to evaluate any expression, any valid expression, sort of like this. Okay. You read your input. This reads at the end of time gets you any white space you have, uppercase and lowercase, then you just do some sanitation of it to go to each character, and then if it's a white space, you just throw it away. If it's uppercase letter, maybe turn it to lowercase, or the other way around, and just keep uppercase or lowercase, knowing your variables are one type or the other. And this way you end up with, what you should end up is one expression like this, but with all the variables the same way, maybe lowercase, no white space, and ready to be processed. Okay? So this is just tedious. I mean, there's no reason why the program centers should consider doing it something. I mean, why put white space in between? It's not going to mean anything. So it's tedious, but you can do it. So you should know and try how to do it so that if you ever come across it, it's not going to break your program or make you go slow. So anyway, let's say we have some mathematical expression. The first thing you have to do is know what that expression, the set of rules that each expression follows. Okay? So a mathematical expression will satisfy some rules. Those rules we can call them grammar. Okay? So what we are going to do is we are going to build a parser for a grammar. Yeah? So what is a grammar? A grammar is, as I said, a set of rules that tells you what a valid expression, what a valid word in a language is. So grammar recognizes a language, the language has words, the word can be, for instance, this thing. So you can think of a grammar as saying which expressions would you be able to evaluate and which they're going to say this is wrong. Like, I don't know, this is just wrong. No mathematician can tell you what this is. Like opening doors and brackets. Where's the next one? Yeah. So, what's the set of rules that follows this one-time expression like this? Mathematical expression like this with plus and times signs is basically the sum of terms, right? So an expression can either be a term, a single term, or maybe it can be an expression plus a term. Right? So I can have a single term, or I can have a whole bunch of terms and then another term, etc. Okay, so this would mean left associative, right? So you know you can write something like this. many ways to interpret this. Some is associative, so you can think of it like this, or some other organization. So what I'm saying here is an expression will be a single term, or either a whole expression and a term. So that's associative. Okay? So I'm interpreting something like this, not like that, but luckily, I know from my math class that the result is the same. Right? So this is what an expression is. It's either a single term or this is a sum of terms. Okay? Many terms. What's a term? So a term, again, it's just like you can have a factor or you can have many factors. Times one times another factor and so on. So again, you have something like this. You can have a factor. Or either you can have third times a factor. Okay? And this again, if you can expand, this is a recursive definition, you can expand it and it just means you can have many factors times one each other. One times the next and the next and the next. And this again is less associative. Again, I don't care. So what's a factor? A factor is, maybe you can have a number, maybe you can have a variable, right? So in this case, you can have numbers or variables. You can have a variable. But here's where the interesting part comes. A factor can also be something in parentheses, something complicated in between. So it can also be parentheses, an expression, the whole expression there. And closing parentheses. Okay? So here you can see these two recursions were sort of stupid, right? I could just write them out. But this recursion is rather non-trivial. You can choose between a number, a variable, or either parentheses and expression. Okay? So the grammar has this property. Normally grammars you can write it this way, recursively, and you can write very simple rules, and even then they understand complicated expressions. So these expressions satisfy that grammar. So this is a term, a term, a term, and another term. This term is two factors. This one is just one factor. This is a factor, and this is another factor. But this factor is a variable, and this factor is an expression. Okay? And again, this is a factor, which is a number, and this is a factor, which is a variable. Okay? So these expressions satisfy this grammar. This grammar is very simple, and then you can write expressions of any length you want, as complicated as you want, as long as you satisfy this grammar, they will be valid mathematical expressions. Okay? And you will be able to evaluate. So in this problem, this grammar is rather simple. I mean, it's the grammar you all know from school, but not necessarily the grammar you have to deal with will be the grammar you know. And many times the grammar will not be defined in this way. The grammar will be defined with words, and you have to write the rules. And I think you should actually write the rules with pen and paper somewhere, so that you know what the structure of your grammar is. Why do I say this? Because the way I'm going to teach you to parse an expression like this is basically follow the grammar. You will follow the grammar structure, what is called the recursive descent parser, and then following the grammar will be very, very easy to code the parser of that grammar. Okay? And here, so I have this grammar, and I would like to take put an expression in here that satisfies the grammar. If I'm lucky, the proper statement says the expression you're going to get is valid, so I don't have to care about I already know the expression satisfies this grammar. It's recognized by this grammar, but I have to understand it. Okay? So what I want to do is understand that thing, and as I said, you have to follow the my input, I will need like an int that will point to the next character in my input that I'm going to consider. Okay? So I will parse this expression from left to right, rather straightforward, and I will always be looking at the next character, and then I decide what I have to do next. Okay? So I can do that because this grammar is context free, and you can decide in a constant number of characters. You look ahead, and what do you see? Well, you see if you see a parenthesis in here, you know you should choose the third option, right? Instead, if you see a character, that may be a variable name, so you choose here. If you see a number, you choose here, right? Or here, for instance, you always know there's a factor, and then maybe if you get a times character, then there's some more factors. Okay? So you should always be able, if you want to do the recursive descent parser I'm going to show, you should always be able to decide one or two or as many characters, the constant number of characters, what you're going to do next. If you cannot decide, then you're going to be in trouble, right? Good. So I'm going to write a very simple parser for this grammar, following the structure I see there. Good. What do I want this parser to do? Let's say I have some values for my variables. See, I'm not saying why I'm interested in values. Let's say I have some values for the variables. There are 6 variables, so let's say I store the value for A in position 0 and the value for B in position 1 and so on. And let's say I have stored them there. So once I have values for my variables, what I have is basically an expression that should evaluate to some number. Okay? If my numbers are integers, my variables are integers, and I also don't have division, and then that's evaluate to some finite. Okay? So maybe before I start, I'm going to say why I want to assign values to the variables. You know? Why do I want to do that? I have two expressions. I can think of them as E1 and E2. This depends on A, B, and this is equal. Or should I test that's equal to A, and so on. So what's here in this test? When are two expressions equal? When they evaluate the same for any choice of the variables I choose. Okay? So for any choice of A, B, and so on, this side should be equal to that side. So then I would say these two are equal. Okay? So checking for any choice, there's an increased number of choices, and so that's going to be hard. But what I can do is just assign some values here, choose somehow my variable. I choose values for them. I do this, and I test. I choose one, I test. I choose two, I test, and so on. So if these two expressions are different, if I do that an infinite number of times, I'm going to get the right answer. At some point, I will say these two are different. Of course, I cannot do it an infinite number of times, so I'm going to repeat some number of times this test. I choose some numbers here and test if this is valid. And if after, I don't know, 100 or 10 or 1 or whatever you like, how many you're willing to do. So you perform some tests. If this condition passes all tests, then you say these two are probably equal because I tested it out and they were equal every time. If these two are different, then they're not. If they are different for one set of variables, then they are different. Okay? how do I choose this thing? I can choose at random, whatever you like, random numbers in range, random prime numbers, whatever you like. Okay? In order to evaluate and test this, I'm actually, we could be concerned that when you evaluate some expression, your numbers get very big. So if you're concerned about that, you should not check if they are equal as numbers, you should check if they are equal on some number n. So again, I choose some mod. Let's do like that. Right, mod m. I choose some mod m. I can even change that from one test to the other, and I test if these equations are, these expressions are the same for some random numbers here. Okay. I know if you've ever tried, but getting two expressions to be the same in many points and not be the same in very few points is rather hard. I mean, like if you want to draw a function like this, and you want to draw a function that is almost the same, but at some point goes like that. These are continuous functions, but the same idea was here. Then this would be sort of breaking this peak, this small peak would be a problem. Especially if you have polynomials like those we are dealing with. So this will work because we are dealing with the functions that are hard to make different in just a very small point. In particular, we're dealing with polynomials on 56 variables, and those are continuous and nice and smooth. So if you want to create something like this, it's going to be hard. You're going to have very different and very long expressions. Okay? If you're equally small, you cannot do something like this. At most, you get something. You have some like over here, and then something that goes like this. And if you choose at random, then maybe you choose something like here, and be able to tell them apart. Okay? So that's the reason why this works. Again, I'm not calculating any probability. I'm just saying you're expecting for this to happen, and we're expecting to do some random numbers that tell you that are around here. And they can tell you if these two are the same. If you choose numbers around here, you can. Okay? So that's a short picture of why we're doing this. So we want to evaluate, as I said, an expression. We will evaluate one, and then we evaluate the next one. And we suppose we have already chosen our variable values, so we just want to get a number on them. Okay? What do we do? So we will put our pointer, the next character we consider, to 0 because we want to start evaluating our expression. And let's say I define some variable which is the result of the first expression. And I just create a function that returns the result of the expression starting here. Okay? I mean, it's very direct. This function returns the value of the expression that starts here. These are global variables because I want them to use them in different functions and not have to go throw it out. So these are global. That means outside main, available to anyone who wants them. Also the position. And that's the key part of this method is the position here. It's a global variable. Different functions are going to throw it forward. They are going to read a character, decide what to do, and then say, okay, this character is done, consider the next one. Okay? So how am I going to write this? I'm going to follow the graph. So this function should return a number. And what should it do? It should follow our graph. So an expression is either a term or a sum of terms. Okay? So the first term is always there. I do not have to check any any character to know that the next term is there. I'm starting an expression, the next term is there. So here I create some result and put and read the term. So this will be the function that reads the term starting at the position possible. Okay, which is global and it has already been set before I start. Good. So I read the first step. What can happen? I can either be here or here. So if I'm here, I ended my expression. Okay? And if I'm here, what I have is another term that's added to this one. And that should be marked by a character plus. Okay? So I should check if the int at the position that the next position I'm looking is the plus character. Then I should read another term, right? And I should add it to my result. So something like this is the first idea we get, but we see that we can have many of these together. Okay? So let's change this if to a while. Okay? And remember, this is going to read the first character as belonging to a term. So I have to update the first character right now, the character I'm going to consider is a plus. I already know what that plus means, that means there's coming another term. So before doing this, I should take, let's do like this. I should take the position, one character forward. I already read my plus. I know that there's an next term coming. Now I can update the result. When I'm done with this while, it's because something different came. Something different from a plus. So I'm here, I finished reading my terms, and then what comes next is not my problem. Okay? Maybe it's the end of it. Maybe it's a part that is closing the expression I have. I'm not there, I'm not concerned about that. So what I'm going to do is return the result. Okay? So I'm writing anywhere. Here and here. I should have like copy and paste. It's not going for it. So I'm going to copy and paste the other way around. You already know what you have to do first. That's there. Can everyone see here? Sort of like, yeah. So this is my function now. So in one place, reads an expression by reading a term, and then when there's more terms, take care of the plus, jump the plus sign, and read the next term, and that's the result. Good. Of course, I've not said what reading a term means. So how do I read a term? I use a function. And the term follows basically the same structure with factors. And it can either be a single factor or a product of the factors. Okay? So I get some result. Which is the first factor. There's always a first factor. To see if I'm here or here, I should check the next character and see if it's a time sign. If it's a time sign, then there's much more factors coming. So, while more factors are coming, what do? I already know there's some more factors. I jump the times sign, and then the result gets multiplied by another factor. Here, and then we return the result. Okay. I should mention before I follow, I'm just being short about this part. As I said, you need to do the operations model. So you do rest plus equals to rest plus term mod the mod. Okay. And so every operation should be done mod function. In order for the number to flow, but for now I'm writing like this, supposing I have some nice way to store this main, or in any case I know the result will be there. Okay? So this reads a term, but it uses the function factor, which I have not said what it is. Okay? So let's write the factor. I can write it here. How do I read the factor? I have three options. Okay? Can either be a number, a variable, or an expression. Okay? So I have to consider all three of them. For instance, how do I know if I have a variable next? There should be a letter, right? Variables are letters, single letters. If they were more than one letter, then I should just, instead of this, I should have a map of words to numbers, whatever. It's not spontaneity, but then now, for example, let's say variables are letters. So if the next character is a letter, then I should basically assign or return the value of that letter. So if the next character I'm considering is greater or equal than the letter A, and the next character I'm considering is also less than equal. See? What I should do is, I already know this is a variable, I return the value of that character. So the character is this thing. So I should put in the left. So if this is A, this is A 0, B 1. So I don't know if this will compile. I'm in the blackboard anyway, so I have to remember to skip this character, which I have already. Right, I'm saving it in small space. Does anyone know if this will actually increase cost? Yeah. Works? So apparently it should compile, and it should give the right result, which is return the value of the variable in position pos. And after that, update position. Okay? So, not there. So that's an option. I've already considered this option. Another option is there's a number next. are easy. I basically do the same, right? For a single digit, okay, it's a digit with the character is greater or equal than 0, and the position, the next character is less or equal than 9. Okay? So this means it's the next one is a number, and it's a single digit, so I'm going to return just I have to return. This is a character. I take out the 0, and this is the number corresponding to that character. And I should also skip that character because I've already read it. So that's that. And again, I return the value and then I increase the position. Okay? Good. So this takes care of these two options. The next option is the next character being an opening parenthesis. Okay? So at this point I may check if there's an opening parenthesis. But as I know I'm not here and I'm not here and the expression is valid, it better be. Okay? Well, let's not check it because we know the expression is valid. So the next character must be an opening parenthesis. That means I'm going to have another expression inside the parenthesis. So what do? I update the position to skip the opening parenthesis. I know it's there. Okay? I have to say the result of reading that expression. I read that expression. That expression will read terms. As long as I have pluses, and it will stop when it sees the closing parenthesis that comes here. Okay? Because I know if this thing will stop the first time it sees a closing parenthesis, then I will just skip that parenthesis and return. Can you see here? Well, it's just return the result. Okay? So,
sorry.
Yeah.
You are sure it will stop at defensive close parenthesis because you didn't put that case in any functions?
Because it was not here, right? Why you see a plus, you just continue reading terms. And what can be, reading a term will be reading every factor that there is. Again, why did this stop? Let's first think why this stops, or when this stops. So this reads a factor, and while the next character times, reads another factor and multiplies. It will stop whenever the next character is not times. That can be, for instance, if I print A times B plus, and there's coming here, C times B. Okay? So this thing starts here, reads the first factor, then finds it times, then reads the second factor here. Okay? And the next character is a plus. So this Y breaks. When it breaks, it returns the result. The result is returned to the expression that called that term. Okay? That expression finds the plus and knows what to do with it. Okay? That expression knows, okay, I've read a term, which was reading this thing. Next is a plus. I know what to do. I read another term. Okay? I read another term, I will read this one. It will stop. Because the next character, what is the next character if this is my string? It's just the stop character, right? /0. If I store a string in an input, in a char array, then I have my my string, and then the stop character. Okay? So it will stop because it finds the stop character, and that's not a task. It will also stop if that expression came in parentheses, because if we find the parentheses, we will not know what to do. Okay? So it will stop when the next character is something you cannot recognize, and that's in this case here. If I know there's an opening parenthesis, I know there comes an expression, and it will stop with a closing parenthesis. Okay, and then return the result. It goes here, and the only thing I need is, before if I try to compile this won't compile because this is like, I define my expression, but it needs term, I define term, but it needs the factors, and the factors cannot be defined upstairs because they need the expression. So you have to predefine them and say I'm going to have this function. So somewhere in your program, maybe here, you can, or here, you can in the beginning declare you're going to declare this function so that the compiler knows how to deal with that. You just say factors. I will be defining factors. I will be defining terms. And I will be defining expressions. So in fact, only this one is needed. If I put downstairs the expression, then above that there and above that the factor, then I really need this one. Say I will be defining expression. But anyway, this is in that way I first tell the compiler I have all these functions, and then the compiler will know how to deal with the recursion of this. Okay?
This all works with times over plus, right?
I'm not sure this will work. But yeah, so this
I think plus times and plus have the same like when I have 1 plus 2 times 3. I have 1 plus 2, then times 3.
yes. So this expression does not work with the product statement. It works with an unrun statement that is reasonable.
But the product statement
so in that case, we just need one thing and read it. That's easier. But let's say our problem was follow the actual grammar from so yeah, I think anyway, this is.
I think the solution is just to add the expression definition, just add another expression times term.
Yeah, I could just put everything in one function, but then I would defeat the purpose of telling what the grammar is and how to get the result.
Yeah,
so I find this is the interesting example. The problem can be solved. I mean, if the problem said you have to read from left to right, then it's probably a little easier to do it. Yeah.
Does this work? Is there a way to handle when the operators have left and right and left?
Yeah, I should. This here I give the recursion. I should call the recursion first. So I read the term and then I recursively add it to the next expression. So I get an old right expression and last. So yeah, I can deal with that basically changing the order inside as well. Okay, but anyways, this is the example of a very simple parser for a mathematic grammar, including class and types. The point is, this can be, the only thing I want to show you is this. This follows the grammar. I don't know if you notice, the recursion follows the grammar very close. So whenever you have a grammar, you just build the parser following that expression. So that's what I want to say on this. Okay? This example is just 2 operations. You can have as many as you want. You can have a very complicated grammar or a very simple one. The idea is you follow the grammar with your parser, and it will be very easy to code something that evaluates the result. So if you want, you can put this thing, try some numbers, and it will give you the right result, as long as there's no overflows or anything like that. So you can solve the problem that involves evaluating There was also, for instance, yesterday there was also light bulb testing, so that defines also a grammar. So that problem defines a grammar that's like. So anyway, with this I finish my parser of mathematical expressions in class times with the right or the mathematical way of associating them. There's other grammars. For instance, light bulb testing had a grammar which was basically a list would be a number or it would also be number space and list and numbers let's call them terms. A term was just could be a number, or those would be parentheses, a list, a time sign, and a number. And numbers were some K. They were actually basically the number written. That's something in the range of 1 or 0. Okay? So this was the grammar for light bulb testing, and basically what they did is this list. This means just repeat the list as many number of times as it says here. So you could extend this list and you have just a list of numbers, and then you say this is the time. The first one is the amount of time you spend waiting to turn the light bulb off. So the light bulb starts on, wait some time, turn it off, wait some time, turn it on, and so on. And you want to know how much time you have to wait until the light bulb exploded or was broke, and they gave you just the number of time the light bulb has to be on to break. Okay, so you basically have to build a parser for this expression and see how much time you have to let go on until that the light bulb explodes. But the first step was recognizing a grammar like this, building a parser, and then inside that parser we have to work to see how to count the amount of time that the light bulb is on and the amount of time the light bulb is on. Okay? So what I said, I worked with one grammar which I expect you to know, and you surely know, basic grammar, very basic grammar. You can have other grammars. This was defined in the problem statement, and the meaning of it is defined in the problem statement, but you can work with it exactly the same way, right? You can just build a parser using functions to read each thing, and then the interesting part is realizing when I'm evaluating a mathematical expression, it's easy. I can just sound, I have those operations, but then understanding what this operation here is, repeat this list some number of times and tell me how much time will that light will be on or off, and doing that is the hard part. So building the parser here is just the skeleton of the solution. What's inside the parser, the operations inside the parser, is the core of the problem, and there's where you have to work. Okay, so usually the problem will not be just parse this expression and evaluate it or tell if two are equal. I did not read. I was hoping it would be something more interesting grammar. But anyway, my point with yesterday's problem equivalent was I tried to show you this exists, and if you don't know how to parse these things, then try to do it once for a very simple grammar or something like this, and then if you practice a bit, you'll be able to go past the first step in many problems, because sometimes you see an input that you cannot read, and if you cannot read the input and understand it, you're never going to solve the problem, okay? So if you get some expression following a set of rules, and you don't know what that expression is going to be, or how to evaluate it, you're done. You're never going to solve the problem, okay? And if you're going to spend 2 hours writing your routine to read the input and understand it, then it's also not going to work. So this is a very simple way to read expressions that follow a grammar, okay? There's many problems that need or that require you to build something like this. So just, as I said, write the grammar, really actually write the stuff, and then write the code that follows that thing you wrote. Okay? Good. So that's it for parsing. If you want, we can discuss problems from yesterday or some other day. No? Problem?
Paper.
Paper presentation. Okay.
Prediction.
Sex prediction. All nice problems. Yeah.
Pockets.
Pockets. Okay. So I'm going to start with pockets because it's the one I'm going to talk about like 5 minutes. Maybe. Same thing with label testing. Pockets is a hard problem in the sense you have to approach it with some strength. You know, you're going to solve that problem. You have to pull up your sleeve and start beating it up. Same thing with label testing. You have to really solve it, or else you're going to stop it. So pockets is a word finance problem. As I said, sometimes word finance problems are not hard to understand or even to code. But I mean, they don't require anything special, but they require you to actually be there and do it right on time. So you should try it because it's the kind of problem you're going to face. But nobody can tell you other than yourself. I'm going to try it, you have to try it a few times. So the idea of pockets is you have I think it was square piece of paper. You can take some sides, right? Take this part, and then flip this over, and then maybe take this part and flip that over. So the paper starts to fold, and that folding will end up when you have some very tall column of all the papers inside. So I saw some of you yesterday trying with the paper, that's nice. You can just start folding it, and when you're done, you'll have, I don't know, if you have just 2 pieces, you'll have something like this, right? But maybe your folding goes like this, and you fold it many times. Okay, I'm looking it from the side. I'm thinking it was folded this way, and then maybe it was folded the other way around. In some sense, you're going to have something like this. And what they ask you to do is count how many pockets there are. So pockets are these things. So when I folded my paper, and I'm looking from this side, I have 5 pockets, and then obviously I should look it like this, and you will have, so I rotate it, and you have other pockets on other sides. Okay? So I should count the number of pockets there are in a folding after I've got a single all the paper in one place, in one small square. Okay? So the way to solve this is just go ahead and fold the method. Okay. The way I implemented this is you can think of each square as being at a given position. Okay, so square this will be square 0, and maybe you say it's at 0, 0, and then this is square 1, and then it may be at 1, 0, and so on. But the nice thing to do is to avoid dealing with half integer coordinates. Just multiply by 2, and you say this is 0, 0, this is 2, 0, this is 4, 0, this is 6, 0, and so on. So that way the lines in between are odd numbers, and the coordinates of the squares are even. Same thing for the columns. So I would probably think something like that, x, y. Anyway, you have squares that are points, and you have to fold them. So you can basically take a map and say at point, I will take a point, so I can order my points by x, y. I create a structure of points that has x and y coordinates. I define an operator minor in that structure to be able to put them up. And I will take the point and give you a vector of integers, saying the squares that are at this point from bottom to up are these ones. And I have an ID 0, 1, 7, 9, 12. So this will be the basic structure for your solution. What you do is initially you put all the points in all the squares at different points, and then you have to flip. So whenever you flip, for instance, this side, all these points stay where they are, but this one will get taken away from the map and put in the vector, the end of the vector of this guy. And this one will be put in the end of the vector for this guy, and so on. So you have to build that function. You have to take care you'll have some structure representing the squares. So the position of the square is here. I will know because it's in the map. But I have to keep other data. The most important data I need is the number of times it was flipped horizontally or vertically. Okay? Because I know this square has 4 sides, and I know, for instance, this side is pointing that way. But when I flip, that side is pointing the other way. And I should keep track of that because I have this thing. I will be needing that information. So I will need to see, to have maybe a rule like that, and this will tell me if it's true. In 0, it's been flipped in the x direction. If it's true in 1, it means it was flipped in the y direction. Okay? So this information is something we need to take into account. And in order to do the next step, you will also need to take into account who his neighbors are. Okay, so this guy has 2 neighbors. So 0, 1, 2, 3. Square 3 has neighbors 2. 1, 2, 3, 4, 5, 6, 7. And 7. And it will always keep those neighbors, right? The paper is not cut. So you will need to keep track of these neighbors, or just store them once, because when you're going to, in the end, what you're going to get is you're going to get, when I stop folding the paper, because I have only one point, okay? What I get is just the list of the squares in the order they are from bottom to top. Okay, so let's say I get this list. Pretty sure this is not possible. Anyway, so, I don't know, maybe the computer better. But when you get this list, after you finish folding your paper, what you see is you'll have to see each of the 4 sides and see, okay, so who's pointing that way? So who's the neighbor of the square number 3 that way? It has no neighbor, but maybe if I flip it, then that way means neighbor 2. So that's why I need the flipping. Okay? So I have to see all 4 sides, and let's say in one side I see that I have 3 and 7 are neighbors, so that means here there's paper. And maybe I see these 2 are neighbors also, which they are never going to be neighbors. So maybe I find these 2 are also neighbors when I'm looking from one side, and then this means there's no pocket here, no pocket here, 1 pocket there. But maybe you had 1, 2, 3, 4, 5, 6, but maybe you had the 6 before. And if the 5 and the 6 are neighbors, then there's paper here. And then these are not pockets, because there's paper all over them when I look that side. So the trick is, first, you just simulate the folding, and you get the list, and you get the neighbors to each side, taking into account the fitting. And after that, it's just the parameterization. Okay? I can think of this thing as meaning that. Okay? So the pocket would be here. Whenever I have 0 open parentheses that I need to close. Okay? So that, in this case, that's the pocket. These are not. Good. So the result is you fold the paper, you get the piece, that's the tedious part. You have to deal with this, you have to deal your folding, you take away from a map, you put in another map, then you take that map into a new one, whatever. However you want to build that, I can show you code that you will not understand. I don't understand it now.
Yeah, one question. When you say, for example, that 3 and 7 are neighbors, so they have an arc. So that will depend on which way you are looking at, because if you fold this way, they have paper, but if you fold the other way, they don't.
If 3 and 7 have an arc, they're both looking the arc is both going the same way. But yeah, it will depend on the side I'm looking. Okay, so if I have this is 3, this is 7. So if the arc going from 7 to 3 is that way, then the arc going from 3 to 7 is that way. So when I look that way, I will find the arc twice. I will find it from 3 to 7 and from 7 to 3. I don't know if that's your question, but yes, each side I'm looking, it depends if I have to take into account that arc or not. They are neighbors, but I should join them only if that arc is going that way. So this arc is going to be moved when I do that. Okay? Sorry, when I look this way. So when I look arcs that go that way.
Well, but actually, if 3 and 7 are folded, they are folded and it's when you look from up or from down.
I was not meaning this drawing is, the thing is if I'm here, I don't write but then I have that superpose and I cannot draw it. Okay? But the idea is you have to keep track of the order in which they appear, how many times they've been flipped, and that will be enough information to tell where, to which side each neighboring is. And that will give you a parameterization, and the points where there's no opening parentheses to be closed, that's the pocket, that's what you have to count. Okay? So I think the nice idea is thinking about it as a parameterization. The other part is just working with maps and doing the things right. Okay. Okay. Try that problem. It's going to be sort of challenging to get the thinking that right, but it's nice to actually go up and hold the paper and then count the pocket and say you're right. So you want it mathematics. sales prediction. One more I don't remember. And let's start with mathematics. So mathematics, you choose a set of any numbers, then you calculate the sum. And it gives you n. Then you calculate the LCM. And then you forget your numbers. But you know n and you know m, and you want to know how many ways you have chosen the a's in order to have n and m. Okay? So here the bounds were n and m under 1,000, k under 100. Okay? So as I said before, whenever you have a problem with LCM, pays off if you think about the prime factorization of the number, and you think about saturated primes and non-saturated primes. So the number that is under 1,000 will have few factors. I think it can have about 7 or 8 factors. And it will have few divisors. It will have sort of I think the number with most divisors below the 1,000 is 840 plus 32. So these bounds, you should supplement them with the number of divisors of n. And the number primes, different primes, again, small, I don't know which, let me see exactly how they use. Different primes, 4, right? 4 different primes. So hardly 2, 3, 5, 7. Yeah, that's probably 210, and then maybe another one that is over 1,000. So these are bounds you need to take into account. And once you know this, because you look at them, just to complete the problem statement, you see, okay, I have n. Involves an LCM, I should see what its prime factorization would be and how we would compose. So you know that every number here should be divided. So every number here should belong to a set of at most 32 numbers. Okay? So you've already constrained this set as only divisors of n, because n should be divided by each one. And there's at most 32 different numbers here. Moreover, there's at most 4 different primes in n, and 4 different primes in each one of these. Okay? Once you know that, you can basically start thinking as, okay, I want to do this, and I have a bag of numbers. My bag of numbers is the divisors of n. So let's say I have this set of divisors of n. This is my bag of numbers. I can take any number from here as many times I want, and I can put it in another bag, and then that bag should have a sum of n. The extra constraint is the LCM of all those should be m. So I should deal with that specifically But I mean, talk about types of numbers. Mainly, I mean, the problem of choosing some numbers in order to sum something is known as outside, right? So that's the NP problem, and the complete probability or something. No idea what that means. It means it's hard. But it's not hard, and you should know it's not hard in some special cases. Okay? Special cases that include all the ones where you're going to see, except the ones where you need to factor. So, anyway, the thing that makes this problem easier to solve than the hard problem that you see in abstract when you go to Wikipedia and it says it's very hard, you cannot do it in polynomial time. Well, the thing that makes it easier to solve is these are discrete numbers. Okay, and the sum of them should be rather low. So there's a dynamic programming solution using that these numbers are few, they have little precision, by meaning you can have discrete intervals between them, and the sum is small. So how do you solve knapsack? I will, at this point I will forget that I need the LCM. I mean, I just have a type of numbers and I want to sum them. I can even forget I want to count the ways I need to sum them. I just want to check if it's possible or not. So how would I do that? I would define an array of dt from 0 to n. Okay. Let's say I want to count the number of ways. Okay, that's not the simplest problem ever. Just count the number of ways to sum n given these variable numbers. So what I do is I initialize these to 0. I know 0 ways of building any number from 0 to n, except for the 0. The 0 can be built with the empty value of numbers. So that's what I know. So this is initialized to 0, but dt of 0 equals to 1. There's one way of doing the value that sums to 0, and that's the empty value. And that's the only way. Okay? So what do I do next? I will just go and how do you guys say this? Invariant. Well, the invariant here is whenever you're going to see a sum, you're going to be sure you know all the ways to build that sum with your numbers. So that would be the invariant for our argument. And anyway, it just means you're going to scan from smaller bugs to bigger bugs, because with bigger bugs can only be made with smaller bugs. So if you know that we cannot make any new smaller bug, then you know how the bigger bugs will look like. That's the idea. So I can go for I from 0, I under n, I plus plus. I will consider I is the sum of my value. Yeah? And I will only do something if I know that value can be made in some way. So if my array for that sum is greater than 0, I should do something. If it's 0, then there's no way to do that value, and there's no way I can use that value to do another one. Okay? So let's say I go over the sums, I find a sum that can be made using maths. The first one I'm going to find is obviously the 0. What do I do? I say, okay, I have this value, I know how many ways it can be constructed. What I do is I try to put any number of my set in there. Okay? So for j equals 0, j under, what numbers do I have? These ones. So the numbers of the meters of n. And what do I do? Let's say I have calculated the jth divisor of n, and it's stored in an array of divisors. Div j is just the jth divisor. So div 0 maybe 2, then div 1 can be 4, then maybe if my number is 12. Right? So if n is 12, the divisors, this array would be 2, 4, 3. Whatever. Could be sorted, could not be sorted. Or yeah, 1. 6. As you can see, when I need divisors, I go to the computer and I just calculate it. Anyway, I have them here, and they're all there. I did not write that down by typing. I use the functions I showed in the first lecture to factorize them, and then to build the list of divisors of it. Right? So if I use that function works, or at least it makes you the 6 there. What you have to do is try to add this number to the back. So adding this number to the back means take I and add the jth divisor. Okay? And what do you want to do with this? You want to say I can build this back by taking any value from here and adding one number. So I will say dp of I plus dj I increase the number of times I can do that in dp of I. Okay? Of course, I can do this if I plus d of j is lower or equal to n. Because if not, I may go over an array or whatever. Okay? So this solves the problem. When I'm finished at dp of I will have how many ways I can build the value of I weight I. Okay? How long does it take? Just n times the number of divisors of n. Okay? So this is the solution to the very basic and classic. Yeah. Okay, so this is the solution to the very basic knapsack problem. I hope you already knew this. But if you didn't, then this is the first thing you should know about knapsack. It's a hard problem in general. It's not hard when you have discrete values and some are small, and there's huge numbers of variations of the problem. So what we're going to do is start to update and change the solution to take into account the two constraints we're missing. The number of terms I should have, and that the LCM should be n. So taking care of the number of terms is the easiest part. Okay, so this is one solution to another problem. I am going to solve now the problem I want. Or a problem that is close to the one I want. Okay? So how am I going to take into account the number of elements I have in my bag? I will use a dp of I, say, k, the weight of the bag. And this is going to be the number of elements in it. So I'm going to store here the number of ways to build a bag of I elements of K elements that weights I. Okay? Updating this thing is really easy, right? So I go over all possible sums, and for each sum I go over all possible number of elements. Okay? So it's just adding a 4 here. What do I do? When I update, I'm adding an element, but I'm adding it to a bag that will contain one element more. So let's see if I can. Let's see that go there. Is it clear the way I. Should I write it? Maybe should I just write the end, the final code. So this will nicely take into account that I need bags of a certain given number of elements. Like the result will be stored here, right? So that will be the result, and it's O and not n times this A. So now I have 1,000, 100, and 32. That's all right. Good. Let me. So I have taken into account then this constraint and this constraint. The fact that they are K, and the fact that they should sum n. I should take into account the constraint that their LCM should be n. How do I do that? It's still abstract, okay? I need to adapt my DP. And the way to do that is to store in an extra dimension of my DP. I will say DP of I K M. So I is the sum, K is the number of elements, M is the mass of the primes that have been saturated. Okay, so this is, I think, the nice part of this problem. You have only 4 primes. So you basically can have 2 to the 4 possible masses. Okay? Whenever you are adding a divisor, what do you know? You know that divisor may saturate a new prime. So if that divisor, this divisor here, has the highest power of a prime that it can have, which is easy to check. Okay, so let's say if J saturates the primes should be stored the different primes in some array, and also maybe the exponent of that prime in n. So the div j saturates that prime in n when in n this prime comes with this exponent if n over the divisor j. This should kill all these exponents. Okay? So when I take this and different than 0. Okay? So, well, I really don't need that. So, if when I divide n by the divisor j of n, the result of doing that is not divisible by some prime that originally divided n. This means this divisor killed all the powers of that prime. And if it kills them all, then it saturates. So I can build an array. So if I check this and this is true, I can build a mask for this divisor. A mask of the primes that it saturates, and I can just do, if it's starting in 0, I can just do saying the mask of the primes that divisor j saturates gets an extra 1 in place corresponding to the ith prime. Okay? So when I do that, then I need to update to see how I update here. So as I said, I update the sum to the sum plus the divisor I'm adding. I update these to k plus 1. And I update these to the mask I had or that mask there. Right? Anything that was saturated before and anything new that might be saturated by this divisor gets saturated in the result. So where's the result now? The result is a B of when the back has n, some k elements and 1 to the number of primes n minus 1. So when all of them are saturated, I am sure the LCM with the n. Okay? So this is, as you can see, O n k 2 to the b, and there's always the nose. Because n was small, these two are small and they don't affect much. You can do the calculation and see it's rather small. Okay? So knapsack is a problem that appears a lot. There's a lot of variations. There's a lot of problems that do not tell you this is knapsack, go ahead and solve it. But you have to think about them. It's usually nice to start thinking about the singular problem and then start adding like the structure that you need. Okay? So at least that's my solution.
Do you think there is like
Okay, what?
faster algorithm? Because I did exactly the same, but instead of using the 2 to the p states, I use another number of divisors.
So you
But
already
otherwise it was exactly the same. And it
You use
seemed to be
the
only a
LCM.
factor of 2.
sorry?
It seemed to be only a factor of 2.
Okay.
Like from 16 to 32. And it got clearly. And it was like the same code and everything.
Maybe there's some. I mean, the faster algorithm probably calculates all the values yourself. You know? Well, you can recalculate, but I don't know. This looks pretty much like knapsack, so I would be surprised if there's another formulation that is different. Like that's one of the properties of empty complete problems, right? If you can formulate it in some other way and you show its equivalent, then you can solve both at the same time. So I've shown this is knapsack with some constraints. Obviously, that makes it not empty. But if you show another way, then in some sense it should be identical to some subcase of knapsack. There should be some identity between any solution and something else. But maybe there's a completely mapped solution. And then, for me, this problem is knapsack. That's what I have. So those who solved it, do something like that? It works in solution set. Yes. No? Okay. Now, time, size prediction was another one. So that, is this clear? Please go ahead and solve problems using knapsack. I was pretty sure I already used the problem with knapsack this week before. So I now forgot to maybe it's one we did not solve. So sales prediction. Sales prediction gave you the recurrence of order R, which is S of n equal to 1. The linear recurrence of order R, the ones I taught Monday, and it asks you to sum all the k elements. Okay? So we want to sum for S, K, S, N, K, alright, 1. Okay, so the k elements get summed. So when n is 1, I get k, 2k, 3k, and so on. Okay, so if I want to calculate this, in this problem k was sort of small. I think k was close to 8. That's not really important. We see this bound relevant. This is the interesting bound. I don't know what it was, but it was really big. It's a 9 maybe. Okay, so this is the hard one. So, if you remember I said recurrences had a way to be represented using matrices. So, what I'm going to do is I'm going to build, of course you are given the coefficients and an initial state. Let's call it S. R, right? So the R first element needs to be there where you do slot calculating. So what is this? R minus 1, so on. Okay, so I will call this thing the vector S R. As I said, I am building a vector that contains R and the previous R minus 1 element. So that's the initial vector. Each vector I write. So what's the vector? Sn. It's just Sn and Sn minus 1 and so on. S and minus R. So that's the vectors I'm going to use. And I am going to act on these vectors with a matrix. Okay? So the matrix I'm going to do, I want the matrix. I want to take vector Sn, act with it using a matrix, and get Sn plus 1. Okay? So I want to build this matrix here. So how am I going to build it? I want them. So this will be the last element. I want to put something here as a matrix. When that matrix acts on Sn, it should give me this. So one thing I should note is the only hard element to get is this one. Okay? So the next one is the only one I do not know. All the other ones are stored in here. Okay, so this one here goes here. Okay, so all these ones will be stored here, but the next one has to be calculated. So how do I calculate it? I know I'm going to multiply this way to get the first element here. So I just start and take A1. So A1 with Sn, A2 with Sn times 1. So the sum of this and this will be this one. So that gives me the order in which they should be put. A2 and so on to AR. So when I cut AR with Sn minus R plus 1, the sum is right. Okay, so that's my check. And then so this so on is just the formula for the next element given the previous one. Okay? So this line, this row, represents this formula. All the rest of the matrix is just addition, it's just auxiliary work. Has to copy the rest of the vector. Okay? So it's not, it's just doing there some hard work, but not really, it does not really change much, right? In a sense, I just need to copy this element here. So in the second row, I need the first element, and the 1. And all those extra elements don't do anything. For the next one, I need to copy this one. So I put 0, 1, these zeros up to the end. This will go on. And when I finish, I will have all zeros. Because I'm going like that, I have a 1 and a 0. And 0. Okay? So I have the first row has the structure of the recursion. The lower diagonal will have 1s. That's all I need. So if I do my hand is this matrix multiplication by a vector, sorry, a vector multiplication by a matrix, I do the same and give me this vector. So that's nice, but essentially lets me take a vector. From the previous vector, I get the new vector by a matrix multiplication. Okay? This is what I'm going to call A. So the first thing you should note is the part of skipping to the next K. I also some escape, S to K, X to K. Skipping is now really easy. As I said, if you want to do this many times, just apply A many times. Just exponentiate A. So I'm going to build a matrix E that is just A, N. Okay? So what does it should be an EK? Okay? So this matrix, when applied to one of these, will just skip my K element. So if I have S n, and I add with b, I get s n plus n. That's a vector. Right. So it just raises all the indices kn. Okay? I can compute this using modex. Anyway, because k was small, you don't do it just by hand. I mean, iteratively. But maybe k should have been 10 to the 9 also. I don't care. So I can compute this using modex. So this bound, I don't know why they put it there, but it could be a much bigger number because I can just compute this with modex. The matrix is rather small because R was also small. So I can take R cubed, there's no problem. Okay, so exponentiating is O R cubed dot K. As you can see, K is only inside the loop. Good. So now I have to take care of the sum. So yesterday I saw some people trying to go the mathematical way about it, trying to work with this expression. I would not do that. If I have a computer and try to use it, then what I'm going to try to do is sort of extend this in order to deal with the sum. Extend the triplet I done here in order to deal with the sum. Okay? Just as a note, I can think of this now as another recursion, depending on it. But anyway, this would be just understanding what's happening. So basically, I want to sum the elements of a sequence. Right? If this is a new sequence, depending on n, k is fixed, then I want to sum all its elements up to n. Okay? But here, so let's formalize that a bit. Let's call S and K. Let's call it F N. So let's say this is a new sequence. Okay? What do I need? What do I need to define a sequence? I need the matrix that takes me from one to the next one. Okay? And that matrix is just B. Right? So B added K to the next, added K to the number of things I had inside. So that matrix is just B. So what I know now is that F n plus 1 is just B at B on F n. Okay? So as you can see, I'm dealing with vectors, Fn. These vectors have size R because this matrix is R times R. Okay? So this would be the recursion. This encodes the equivalent information that is here. What I'm missing is the initial condition. The initial condition should be the first one here, F1. Okay? So who is F1? F1 should be defined here. This S K as a vector. And who's S K? It is A, K minus 1. Is R. Right? Something like that. initial condition was SR. Yeah, well, let's flip it. Yeah, that was why I was doing the other way around. So there's some. Let's be more precise. Let's write later. So I need to, in some sort of sense, write the vector containing in some special position Sk. Okay? Then the next one will contain. So I am going to say F1 as a vector. Okay? Contains the Sk element here. The last one. Okay? So this will be my definition of the X. And here I need F1 and so on. And this vector has to have size R. So it will be S. That's R. Okay? So this will be my vector S F1, and I can build it now. So you can believe me, I'm building this vector by acting on SR. Remember, SR had a 1 here. I act k minus 1 times, and I increase each element k minus 1 times. So this becomes this k. Okay? So I'm changing the definition so that the first element is k. It's the first from below. That way I do not have to deal with the fact that he mentioned that k may be inside or outside your vector initially. Anyway, I want to leave k below, so I act with a k minus 1 times on its arm. Remember, this is a acting k minus 1 times on a vector that is f1 SR. Okay? I increase everyone by k minus 1. So that's what I mean by f1. Okay? And then I need to sum here of the fn, the last. So this will be the last element in the vector of f. Okay? So that's just a trick, because you're initially in SR, there's two options, SR as a vector at SR on S1, and you do not know if SK is here, so SK will be here. If it is lower than R, or it could be here, if it is greater than R. So what you do is you just lower this vector up until you reach SK, and then you know it will always be downstairs. When you act with a to the k power, you have s2k downstairs. Okay? Ever recall that? Yeah. So if you think about it, I think it simplifies a bit the next part. So I have a vector now that contains the elements I want to sum. They are the ones downstairs in each vector. And I want to sum for n equal to 1 to n equal to n. Again. Okay? What do I do? There are too many, so I cannot go one by one. So what you have to do is, you have to extend your vectors and your matrices to deal, to store the information you want. Okay? So let's erase it because we already know what A is. What S N was. We already know this. So what we want to do is extend our vector. Okay? I want it to contain more information, and I want my matrix that takes me from one vector to the next vector to actually update that information. So the information I'm going to extend, my vector, I will call it, I don't know, F prime. G. Gn will be just Fn. So we should have here F there's so this part that's upstairs is just Fn. Okay? So I define it there. This part upstairs is just a copy. And I will use this place to store extra information. What will I store? The result I want to calculate. I will store here the sum of S and K for n equal to I1, n. Very good. This is the gear of here. Right? So this is Gn. Who's G1? G1 is just F1, this guy, and you have to sum the sum, you have to have the first here the sum from 1 to 1. So I just repeat the last element. There's only one and it's done. Okay? Good. So this is my G. I have my G1, I need to know how to go from G1 to G2. So let's say I have Gn, and I want to add something and get Gn plus 1. Work? This guy, that's right. Basically, this guy will be downstairs in the sum I want. Upstairs we have that. Here we have So I want to go from this vector to this vector. Right? What do I do? Remember, this is F. And this is Fn plus 1, and this is Fn, just that, Fn. Okay? So, almost all of my matrix will be basically the matrix B that takes me from Fn to Fn plus 1. So here I just copy B. So this is R, and this is R columns and R rows. Because I extended my vectors, I have one more column and one more row. And I only need to complete this guy. So how do I complete this guy? So the idea is I basically need the previous result. So when I compute this guy, I start from the time like that. There. And you can basically put the 1 here, and you can just sum all the elements up to n. Okay? And then you need to compute from these guys, like that. You need to sum the next one, n plus 1k. But you can see n plus 1k is just here, it's the first element. Okay? To compute this guy, I basically take, so all these will be zeros. I do not want to affect the calculation. There. So when I compute this guy, which is the next one I want to sum, sorry, this guy, the one I want to sum, compute that one, I'm going to do this. In the last row of B, I am going to do this. Okay? So I need to sum this one. It needs to come inside here. So this row here gets duplicated there. Okay? When I calculate, when I go like this, I sum some coefficients there. That should be this guy, because it's the same calculation that I did for the previous element of my vector, and then that gets added to the last one. Okay? So this gives me how to go from G to G plus 1. Okay, so from Gn to Gn plus 1. Depending on how you build or extend your vectors, whether you take the interesting element in the beginning or in the end, you will have different ways of creating this matrix. Okay? But the idea is that, I don't think my coding is expected, sorry. But this is the correct way of doing it. Okay? So what now? How is the result is just this. To get our result, what we have to do is we basically have to sum everything up to Gn, right? So to obtain Gn, we have to add. Let's call this whole matrix n equals the matrix. Then n from G1, and we have to add n minus 1 times. Okay? So these were vectors. Right? And when we add to them n minus 1, we get this vector. The last element of this vector is the sum we want. From 1 to big N of all the n. Okay? So this is one trick that you can do when you use models and matrix representation for linear recurrence. Okay? The thing is take home. It's not, I mean, keeping your mind, not really the steps. I've been through you can redo them later if you didn't get them all right. What you have to do is keep in mind you can extend your vector with more information, and if you can keep track of that information from one to the next one, just in one step, you take care of one step, then you exponentiate, and then you'll be taking care of as many steps as you go. Okay? So that's the interesting part. You extend with more information, you take care of a simple problem which is going from one step to the next one, and then exponentiating gives you the result you want at any number of steps in logarithmic time. Okay? Someone asked for paper presentation. Yeah. Someone else wants paper presentation or someone wrote it on. Yes. That's not something that 10-20 minutes, and that's the last me or something for me something there. Okay. It's not enough for me. That's not going to fit in 20 minutes, so I can talk to you how to do in person. So I can show you all, and it's not going to be less than half an hour. Okay. Any problem I can cancel? Find out what stuff. Center problems. Another one I can just leave it over. But I can show you many of them. Let's talk about flows. You're asking for what problems, so I'm going to go with the easy one, which was paper presentation. So the constraint was you had before I raised my mount. Okay. Another one. I can talk about it with you later. Geometry is always to understand the concept. Paper presentation is nice because it's short. Its counting is 5 fraction. Counting nice. splitting, so you have n equal to 12 and team scientists total, and you need to split them. But the fact is, to split them, you cannot put in the morning someone who is needed, or his talk is needed as a previous step for someone in the afternoon, because people will eat and they will forget what they have heard, which is sort of true. So the idea is you have to put scientists that need each other the same day, and you need to put them in the correct order. So if A needs B, then B will be first, then A, and they have to be either both in the evening or both in the morning. Okay? So I need to count the number of ways to do that. The first thing you should think is this number is really small. So you should probably try all possibilities of splitting the cycles. Okay? So even it's not even 2 to the 16 because you have to split them into 2 equal groups. So split them in all possible ways. How do I do that? I use masks, bit masks. I can generate all the masks that have n bits on and n bits off. Okay? So in order to do that, I can use DFS, for instance. So what's going to go in my DFS? Which scientists I'm considering? So the current scientist. I should keep track also of the groups I have formed yet that can be in a mass. And I should keep track of how many scientists I have left to add in my mass, maybe if I don't want to count each time. So for instance, this is a nice set of parameters. I will have the current scientists and I have the mass of those. There's a 1 in the position of that mass for every scientist that is in my group. So I'm taking scientists one by one, or saying I take you or I don't take you. And when I finish, I have to have this equal to 0 because I have to have taken all of the other scientists. So when I call this, I will call this with sort of like DFS, considering the 0 scientists with the 0 mass and F. Okay. So that will be my call. And what do I have to do? Basically, I have to check if I, in the end, so if the current scientist is the end, which does not exist because scientists are numbered from 0 to n-1, then do something. We're going to see what comes here. Else, I have to consider 2 possibilities, right? I'm considering this scientist, I have to take him or not take him. Okay? So not taking him is always possible. DFS. I go on to the next scientist. I take my mass and I give it as this. And I've not done any insight, so going ahead and saying I'm not taking that scientist, but I also need to take into account the fact that maybe I can take this scientist for my group. So if I have some scientists to take, then this is non-zeroically true, then DFS and to the next one, I take take my mask and I store it in one in the current position, and then I take the step. Good. So this will reach here. At the end, I may have I have curve equals to n. I have my group, but maybe I have someone left, which is not nice. I do not want to have groups smaller than n. So only if there's no one left, you should calculate something for this mass or for this group. Okay? So what should I calculate? Let's say I have some, so this is assignment main. I will be having some result, initialized to 0. Probably I need some non-numbers there. I think it was small, whatever, take care of the overflows. But if there's no one left, this is a valid group of n scientists, which I have to count. The way to count this is basically just my result. I will add the number of ways in which I can order the guys in my mask for the morning, for instance. So count the number of ways I can order these guys without breaking the fact that one should go before the other. So count the mask. And that should be multiplied by the number of times I can order the guys from the evening. The guys from the evening, who are they? They are the ones not here, right? So the way I do this is 1, I can. This is 2 to the n power. I take 1 from it, it's all ones up to n. And sorry, with my mask. There you go. Right? And I use the underscore here, why? I'm going to memorize stuff, okay? So the number of ways to order something is factorial. N is not an unrelated stuff. M here is less or equal to 8, which is less than a million. So 8 factorial is okay. But it's not okay if I do it 2 to the 8th times or 16 taken by 8 times. So it's okay if I memorize, it's not okay if I don't memorize it. Okay? So what I'm going to do, I'm going to have maybe a long array of count stuff. And it should have sort of this size so that any mask or any number of scientists can go in there. Okay? I will initialize it through -1. Yeah. And whenever I fill that, I will change the value. And then I know the value was already calculated, you don't need to calculate it again. As always, there's memorization, they have the same structure. I mean, I have lockdown, count with an underscore for me, and then I get the mass, and I have to see in how many ways I can count or reorder the guy in this mass. Okay, so again, if count of this mass is -1, I've not calculated it with also else return. Right? So what do I do if I have not calculated? So the first thing I should do is check that the splitting is correct. Okay? I should not count anything when this mass and this mass have guys who need each other. Okay? So the splitting should be. So check. Let's say count of my mass is 0, and then only if I check that mass and it's correct, it's a correct splitting, I will add stuff to it. Okay? So this function, what should it do? You should check that every guy that is needed by a guy here is also in that mass. Okay? The way to do that efficiently is for each guy, build a mask of the guys he needs. Okay? And then you go over the bits in this mask. Whenever you find the 1, you check that all the guys that guy needs and your mask is the same thing as your mask. Okay? Or, sorry, as the guys he needs.
Don't you have to check something out in order?
So the order is going to be checked here. The number of ways I can do it depends on order. If there's a cycle, the result will be 0 because I will not be adding anything here. So the order will be checked there. Okay? So how do I count the number of ways I can order them? First of all, I should say the number of ways to order a mass that is empty is just 1. The empty order is 1. Okay? What do I do here? I should check who's the last guy that comes from this mass. The last guy is not needed by anyone else. And maybe only people I already have. So the result is I go over all sides. If they are on my mass, that is, my mass in the height position as a 1, this guy, the ith guy, is in my mass. Okay? If I'm breaking my ears because it's going to be done. This guy is in my mass. He can be the last one if he only needs guys that are before him. So if needs I and my mass is equal to the one he needs, so this is the array I was talking about. For each guy, it tells me the mass of the guys he needs. So if I take the ones he needs and the ones I have before him, and it's just the ones he needs, all of those he needs are before him, and I can take him away and put him last. Good. So I just count as equal. Count of this. Count of my mass. I add to it the count So I hope everyone should be comfortable with dealing with bits and bit operations. They are really, really useful. Bit masks are really useful when dealing with permutations. What we're doing here is counting permutations. Okay? So we're taking the last guy and saying if he needs only guys that are already before him, I can take him away and say this is the last guy and I'm here. If there's some cycle or there's something that is impossible to satisfy, then I never add anything here because everyone needs someone else, and then nothing will come. Okay? Sorry, one extra check that goes here. I should check that the other guys do not need P. Right? That's again another check. So I didn't say that check, and there's another check here.
Isn't that check like when you look for the other guy?
Sorry?
Don't you check that when you look for the other guy?
I'm saying this guy will go last. Or maybe some guy before him will need. So that can be, that can work. So I can show you how the check is very simple. It's just, yeah, I have here, it's just, it wasn't my code anyway. So you just go over all the guys and check they don't need me. Okay?
The answer will always be an even number, right? Because combination is more increasing.
So, yeah. I think, I don't know if they asked you for the even number or for the odd number. Like the one I get when dividing that by 2. Anyway, here I am doing all masks 2 times, right? One here and one here. So I'm getting the even number. If I want the odd number, the best way of doing it is just putting 1 here. Then I will be generating only the masks that have a 0 so that they don't have the first guy. If I put a 1 here, I generate only those masks where the first guy is not. And then this mask does not have the first guy, this mask has the first guy, and then choosing the first guy goes to the morning or to the evening. So I don't really remember the word to say one of those. I can check in my code. In my code, I'm getting the even number. Different color for me. Okay? So, well, as I said, let's check. Yeah, basically, this check is equivalent to this check, but here I can check something. So, I'll combine that, combine the correct code, which I'm going to show you. Or I can show you. Anyway, the idea is the idea here. So the idea is you backtrack over all possible splittings, and then you use BP to count possible permutations. So when you're dealing with permutations, it's really, really common to use the mask and say which was, and only keep track of the last element in your permutation, because all permutations that contain the same elements and the same last one will differ only in previous elements which you may not care about, like in this case. So the same kind of TP or similar can deal with traveling salesman problem or other kinds of problems that have permutations. Okay? So people solve it, right? Currently, you can do it some calculations. This just counts. Okay. Questions or answers? I think we're done.